Hello students, welcome to class 12 physics. In this video we are going to solve textbook illustrations. So let us start with 7.6a. A resistor of 200 ohm and a capacitor of 15 microfarad are connected in a series to a 220 volt 50 Hz AC source. So as you can see over here, the circuit has a resistor which is connected in series with the capacitor, and it is connected to the AC source having 220 volt and 50 Hz. So here 220 volt is the AC source, that means it is the VRMS value. So VRMS equals to 220 volt. Then we are given the frequency which is 50 Hz. Resistance value is R equals to 200 ohm and capacitance value, that is 15 microfarad. So convert it into farad, that is 15 into 10 raised to minus 6 farad. Calculate the current in the circuit. So here we are not said to find the maximum current or the peak current or the amplitude of the current. So in such case we need to find the RMS value of the current. So we need to find over here IRMS. Now as we can see over here in the data, we are given RMS, we are given frequency value, R value and C value. So first of all let us see the general formula for the IRMS. So that is equals to IRMS equals to VRMS upon Z, because over here in this circuit we are having resistor as well as the capacitor. So we need to take the impedance, because impedance is equals to resistance plus the reactance. So let us write the formula for Z, that is R square plus XL minus XC whole square. In this circuit we are not having inductor, so the inductive reactance will be 0. So neglecting that, what we will be having is R square plus minus XC whole square, that becomes plus XC whole square. So the formula will be IRMS equals to VRMS upon under root R square plus XC whole square. Here we are not given the capacitive reactance, so taking the formula of capacitive reactance, that is Xc equals to 1 upon omega C, and as well as we are not given the value of omega, so we need to convert that in the form of 2 pi f, that is 2 pi f C. So now using this formula, Xc square will be 1 upon 4 pi square f square C square. So using this formula we get VRMS upon under root R square plus 1 upon 4 pi square f square C square. Now put the values of R, pi, f, C and VRMS. We get 220 upon under root 200 square plus 1 upon 4 into 3.14 square into 50 square into 15 into 10 raised to minus 6 whole square. So when we calculate this, we get the value as 0.755 ampere. So the RMS value of the current is 0.755 ampere. So students, you may note down this numerical. Now second part of 7.6. A resistor of 200 ohm and a capacitor of 15 microfarad are connected in a series to a 220 volt 50 Hz AC source. Calculate the voltage RMS across the resistor and the capacitor. Is the algebraic sum of these voltages more than the source voltage? If yes, resolve the paradox. So first of all, it is clearly said that we need to find the VRMS value, and we are given the value of the resistance as well as the capacitance. Here we need to find the voltage across the resistor and voltage across the capacitor, that is VR and VC. Here we can apply the formula of Ohm's law. We know V equals to IR. So using that formula we can find voltage drop across the resistor, that is equals to IR. Here I we need to take the RMS value, that is IRMS into R. And in first part we have solved the RMS value of the current. So put the values of that 0.755 into 200. When we calculate this, we get the value as 151 volt. In the same way, we can find the voltage across the capacitor. Again, using the Ohm's law, we can write I into R, but here we need to find the voltage drop across the capacitor. So instead of R, we need to take the capacitive reactance. So it is IRMS into XC. Now we are not having the value of XC, so we need to convert that into form of omega C, and we know XC equals to 1 upon omega C. So we can write this formula as IRMS into 1 upon omega C. As well as we are not having the value of omega, so convert that in terms of the frequency. So omega is equals to 2 pi f. Now the formula can be written as IRMS into 1 upon 2 pi fc. Now substitute the values of IRMS, pi, f and c in this formula. So now it is equals to 0.755 into 1 upon 2 into 3.14 into 50 into 15 into 10 raised to minus 6. So when we calculate this, we get the value as 160.3 volt. So the voltage drop across the capacitor is 160.3 volt. Here VR and VC are not in same phase. Hence we cannot make their algebraic sum to get the resultant voltage. So here if it was in the same phase, then we can add it up directly. But as it is not in the same phase, then we can use the vector formula. Here as you can see in the figure, along the x-axis we are having VR, along negative y-axis we are having VC. So this is the resultant vector V. From this we can apply the formula, that is V equals to, we can use the formula for suppose we are having V. So we need to take the formula as under root of x component square plus y component square. So here instead of the x component we are having the VR, and along the y we are having VC. So V equals to under root VR square plus VC square. Now put the values of VR and VC, that is under root of 151 square plus 160.3 whole square. Now when we calculate this, we get the value as 220 volt. So the summation of both the voltage drop across the resistor and the capacitor is equals to 220 volt. Above voltage is equals to the RMS value of the source voltage. So students, you may note down this numerical. Now numerical number 7.8. A sinusoidal voltage of peak value 283 volt and frequency 50 Hz is applied to an series LCR circuit in which R equals to 3 ohm, L equals to 25.48 millihenry and C equals to 796 microfarad. Find the impedance of the circuit. Here we know that impedance for the LCR circuit is equals to Z equals to under root of R square plus XL minus XC whole square. So here we are given the value of R and L and C and F. So we need to find first XL and XC. So let us calculate that first. XL equals to omega L. Convert that in form of frequency, that is equals to 2 pi FL. Now put the values of F and L in this formula. So that is equals to 2 into 3.14 into 50 into 25.48 into 10 raised to minus 3. Here we are converting millihenry into Henry. So when we calculate this, we get the value as 8 ohm. So the inductive reactance is 8 ohm. Now let us calculate the capacitive reactance, that is equals to 1 upon omega c. Now taking that in terms of frequency, we can write 1 upon 2 pi f c. Now put the values of f and c, we get 1 upon 2 into 3.14 into 50 into 796 into 10 raised to minus 6. When we calculate this, we get the value as 4 ohm. So the capacitive reactance is 4 ohm. Now we can use the impedance formula, that is Z equals to under root R square plus XL minus XC whole square. So when we put the value of R, XL and XC, we get the value as 5 ohm. So the impedance value for the LCR series circuit is 5 ohm. So students, you may note down this numerical. Now let us solve the 7.8b. A sinusoidal voltage of peak value 283 volt and frequency 50 Hz is applied to a series LCR circuit in which R equals to 3 ohm, L equals to 25.48 millihenry and C equals to 796 microfarad. Find the phase difference between the voltage across the source and the current. Now we know the phase difference between the voltage across the source and the current, that is given by tan phi equals to XL minus XC by R. So first of all we need to find XL, we need to find XC, because here we are not given the values of XL and XC directly. So in the previous part we have already find the inductive reactance as well as the capacitive reactance, where XL equals to 8 ohm and XC equals to 4 ohm. So now we can apply over here XL minus XC upon R, that is 8 minus 4 upon resistance, that is 3 ohm. We get equals to 4 by 3. So tan phi equals to 1.333. Now we can use the natural tangent table to get the value of phi. So in that we get phi equals to 53 degree 8 minutes. So from this we can say that voltage leads ahead of the current by an angle 53 degree 8 minutes. That is, voltage is leading the current by 53 degree 8 minutes. So student, you may note down this numerical.